Alright, so here's a problem with density of gasoline. So we go back to the first concepts we have learned in this chapter, which are thermal expansion. I want to know by how much the density of gasoline changes when the temperature goes from 0 degrees Celsius to 33 degrees Celsius. So when the temperature is 0 degrees Celsius, the density, which is mass divided by volume, is equal to 0.68 times 10 to the 3. So I'm just going to write this down as 680 because it's easier to follow. Kilogram divided by 1 meter cube. So the density is 680 kilograms per meter cube. That means in 1 meter cube of gasoline, the weight will be 680. Now, if we increase the temperature to 33 degrees Celsius, what you can imagine is that the gasoline will expand. Because it is warmer, substances tend to expand. And what that will cause is that the mass will stay the same, but the volume will be bigger, right? Because it expanded. So I will call this V prime, which is a modified version of the volume. And so the mass will stay the same, but the volume will change. So how do we calculate this V prime? That's when we need to use the law of thermal expansion. So V prime equals the original volume plus a delta V, which is the increase in volume. And this delta V, we know from equation, is equal to beta times V0 times delta T. Here, V0 is the original volume, so that is what I already called V. Beta is the volumic, how do we call it? Volumic thermal expansion coefficient, something like that. I will get the exact word for you guys. The coefficient of volume expansion beta. And you can find this in table 13-1. And for gasoline, coefficient of volumic expansion is 950 times 10 to the minus 6, and this is in degrees Celsius minus 1. And then delta T, we go from 0 to 33 degrees C, so this is quite obviously 33 degrees Celsius. Right, so if we put everything in this equation, we have all we need. We will do it for a volume of 1 meters cube. And there is nothing in the problem that specifies, okay, you have 1 meters cube of gasoline. But we could do it for pretty much any volume. The only thing that matters is how much is going to change. And I find using 1 meter cubes just the easiest choice because density is given in kilograms per meters cube. And so if we use a volume of 1 meters cube, then we already have that number here for the mass. So we will simply use a volume of 1 meters cube as the original volume. It's not equals yet. We still have to multiply delta T, which is 33 degrees Celsius. And this gives a total of 0.03135 meters cube. Excellent. So what is V prime? It is 1 meters cube. We set V here to be 1 meter cube. So V prime will be 1 meters cube plus the difference in volume, delta V, that we calculate here. This is the expansion in volume due to the change in temperature, 0.03135. So at 32 degrees Celsius, the density will now change. The mass stays the same, because temperature doesn't have an effect on mass, but it does have an effect on volume. So here, instead of 1 meter cube, we have 1.03135 meters cube. And so we can simplify this and bring it in terms of kilogram per meter square units. And this is 659 kilograms per meter square cube. So there you have it. This is the density on a hot day when the temperature is 32 degrees Celsius. And now in B, they're asking us what is the percent change in density. Well, this is simply the ratio of the two, so 659 divided by 680 is equivalent to 96.7% or 97%. And so how they phrase it in the problem is minus 3%. Well, to go from 680 to 659%, you had to lose 3% of the original. And that's because 100% minus 97% is 3%. So depending on how you phrase it, this is also equivalent to minus 3%. To calculate the minus 3%, you would have needed to do 680 or rather 659 minus 680 divided by 680. So the final density minus the original density as a ratio of the original density. You have minus 3% of the original density. I prefer to see it this way as 97%. It means after the thermal expansion, your density is now 97% of what it was. You can also see it as you lost 3% of what you had. And I think that's it for this problem. I hope it was clear, and I wish you good luck.